Okay, I want to talk about the new Nobel Prize in Physics on the attosecond imaging, essentially, with the attosecond laser. And this is based on using the wave probability in quantum physics to then be able to image the actual change of charge of the electron. And so, due to the Pauli exclusion principle, the Wolfgang Pauli exclusion principle, the electrons have to be in different places at the same time because of the 1/2 spin, which essentially means that the spin would cause the charge to self-annihilate of the electron. It would explode or disappear. So that way, it has to be it has to be excluded from its from the opposite charge with a different spin. And so this gets you into a relativistic quantum analysis. And so with the attosecond laser, they are able to actually follow the momentum of the movement of the electron in around a proton for an atom, for an element like oxygen or nitrogen. And so how they're able to do this at the attosecond level is using interferometry based on the overtones that are then measured as an amplitude for the momentum, as the energy of the electron. So the amplitude is squared to get the overtone as a beat. So it's the phase difference between the overtones, using interferometry to then calculate the pulse as a attosecond wavelength. And so this invention, this experimental invention, can then be used for a photoelectric effect as a signal, as a computer signal. So it could potentially speed up computers by another 1,000 times. It's also being used to study the photosynthesis, because photosynthesis is based on quantum entanglement. And so if you're able to measure the actual quantum tunneling of the electron based on the changing of the charge, then the movement of the electron as it changes, as it goes through quantum tunneling, is essentially explaining how photosynthesis works. And so if you're able to understand that, then you can potentially manipulate it to then harness the photosynthesis energy, which is a 100% efficiency energy transfer. So this is why physicists are very excited about this attosecond electron manipulation. And the key point here is that they're defining the electron as a wave. And so they're using overtones, which is again from music theory, and then the Fourier analysis, but they can't measure the precise location of the electron as a particle because of the Heisenberg uncertainty principle. So what they do is they slow the atom down, the element, so that the proton itself isn't moving, and then they're able to study the electron. They can single out one electron and therefore trace its precise movement from one side of the particle, or one side of the atom to the other side of the atom. Or they can study the difference between the energy of the electrons for the different shells for one atom. So if it's a higher energy electron or a lower energy electron, they can single out each electron. And so how this fits into non-commutativity is that in non-commutativity, you're not just measuring the energy as the amplitude squared with Fourier analysis, but rather you're measuring the negative frequency and time reversed information before any energy is measured as a collapse of the wave function, before Heisenberg uncertainty. And this is being done with the weak measurements, where they're able to just manipulate the momentum from the future without using an entangled photon, and now they're going to do it with entangled particles. They're going to use argon. And so when you do this, you're able to show the non-commutativity as the non-locality of the future and the past overlapping as non-locality. So as Alain Kahn has shown the non-commutativity, for example, the standard for time is now based on the transition frequency of the cesium atom. And when you rely on the transition frequency, it's now a non-commutative invariance that does not vary due to relativity. So it will be the same anywhere in the universe. And this is Alain Kahn's big point, is that if you're an alien from outer space and you want to try to have the same standard as trying to measure the length of a meter. And so the speed of light, for example, is defined based on the length of the meter. So that's why it's 299 ... meters per second. But in fact, the meter itself will change based on the location due to relativity. And so to get beyond the observer effect of relativity, you have to rely on time directly. And so when they measure time from the cesium transition frequency, they're using actually two different electrons that can be converted into a symmetric commutative geometry. And that's what creates the invariance, is that you're cross-correlating using the Poisson, what's called the Poisson bracket. But you get that from the Moyal bracket. And the Moyal bracket is non-commutative. In other words, as Heisenberg discovered, that the Ritz-Rydberg combination principle for photons being emitted from the electron is a non-commutative time and frequency. So the direction that you measure the photon emission will then change the value of the wavelength. And so that's why you have to rely on frequency directly and not the wavelength. So for example, if the speed of light changes based on what the medium it's going through. So the wavelength changes, but not the frequency. So that's what they're relying on in this attosecond imaging and engineering, is that it was discovered because when they sent infrared light through, I think it might have been argon. There was these overtones created from the electron, and the overtones were in the ultraviolet frequency. And the lady who discovered that, she was part of the Nobel Prize, she realized that if you convert those overtone frequencies of energy into the momentum as velocity with the mass, with the energy, so you have to square the amplitude, then you get the change in the momentum is therefore actually a phase difference as a beat. And so you can, based on the wave mechanics, you can then she verified that the beat is in the Attos. Well, she didn't. It's the same beat. Whether she could determine the wavelength was a different story, but she could measure the overtones as frequency, and then as converted as the change in momentum for the particle of the electron, then has the amplitude as a phase beat. And so all those phases were the same. And so it created a pulse that was the same pulse. And then the second guy who got the Nobel Prize, he created a way to then split that pulse into a delay as an interferometry measurement, and therefore you could calculate the phase change in the pulse. And he was able to do that down to, I think, 600 attoseconds. And so therefore you can then manipulate the actual attosecond pulse as a new type of laser, attosecond laser, that can be used for imaging the change of the electron. And so again, this is a very, very exciting discovery for physics, but it still does not quite tap into the non-commutative non-locality that is being done in the weak measurements that Basil J. Hiley is doing with Robert Flack. But it was also tapped into by Gunther Nimps, who discovered the superluminal sound signal that he says is going on all the time around us. And this is again due to this non-commutative phase of the future and the past overlapping. So normally in the quantum physics, you convert when you assume it's a complex number, and therefore you cancel out the negative frequency when you square the amplitude. But in fact, in noncommutativity, you separate the real and the imaginary part of the complex number. And therefore, the imaginary part has the negative frequency with the time reverse signal from the future. And that's the non-locality that's inherent to creating the charge. That is the 1/2 spin that cannot be directly observed unless you can somehow manipulate just the momentum separate to the position before the collapse of the wave function. That's what they do in the weak measurements. That's also what they're doing. That's also what Günter Knips did with the superluminal sound signal using quantum tunneling with a negative refractive index. And it's also what Sir John Pendry does with the similar experiments with metamaterials and what he calls the Archimedes screw of light. So he's able to turn the light around in a spiral that then has this same negative time or negative frequency and time reverse signal, and therefore he's able to convert virtual photons into real photons. And so the attosecond research is very exciting. It is, because it's based on the same concept of overtones and phase change and the relationship between frequency and amplitude, but it still does not quite tap into the non-commutative, non-locality secret. But it definitely is getting very close because they're able to pinpoint when the 1/2 spin is changing the charge of the electron based on the quantum tunneling. So they're like right at the threshold of manipulating that energy that comes from the change of the spin of the electron changing the charge. So it'll be interesting to see what develops from this attosecond laser technology. Thanks.